All right, as promised, today's the big day. We're going to do a statistical analysis, and now things start cascading. Um, Up to this point, we've been using data to estimate parameters. Our estimate of those parameters are the statistics, and then we've been using those statistics to learn something about the underlying sampling distribution that we got the sample from. But what we haven't done yet is we haven't done a formal statistical analysis. And just to remind us, statistics are our estimates of parameters. Statistical analyses are things that we do with those parameter estimates. And so the first kind of group of statistical hypothesis testing that I want us to think about are ones that are based upon the t-distribution. And so basically any test that uses a t-distribution could be called a t-test. And there's lots of different flavors of things that are called a t-test. A lot of times I think that people maybe don't even appreciate that behind the scenes in a lot of the analyses we're doing, there's a lot of t-testing going on. And so let's remind ourselves briefly, what is the t-distribution? So it's going to be called a t-test because we're going to use a t-distribution. And recall that the t-distribution is the expected sampling distribution of the mean. If you were to go out to that population and take a sample, estimate the mean, take a sample, estimate the mean, take a sample, estimate the mean, we would expect the distribution of all those means to be the t-distribution. And the t-distribution differs from the normal distribution in that it has fatter tails, right? So when our degrees of freedom are low, we're going to have fatter tails. As our degrees of freedom approach infinity, the t-distribution will converge on a normal distribution. So we can think about the t-distribution as the sampling distribution for the mean. We could even kind of more broadly think about what the t-distribution might be useful for, which is whenever we're dealing with the location parameter, assuming that our underlying sampling distribution is normal, the t-distribution is probably going to be the most appropriate distribution to use to model our data and to test hypotheses. And so in general, what we're going to want to do, if we think, let's remind ourselves the t-distribution. Here is my artistic rendering of a t-distribution. Not such a good artist, am I? It's centered at 0, because it's always centered like it's a standard normal. And then again, the width of this, the fatness of those tails is going to be determined by the degrees of freedom. And so what we're going to want to do is we're going to want to take our sample and we're going to test some hypothesis about our sample. And what we're going to do is we're going to calculate what's called a t-statistic. And then we are going to look at where that t-statistic falls on the x-axis here of all our possible values of t. And we're going to ask, what is the probability that I would get a t-statistic that extreme or more extreme if the null hypothesis were true? And we'll go through this and hopefully it'll make sense. But the first thing we have to think about is how the heck do we calculate our t-statistic? And the t-statistic is calculated as our estimate of the mean, the estimate of our location parameter, minus some hypothesized value, whatever our hypothesis is, divided by the uncertainty around the mean. And so the standard error of y. Again, since we're interested in testing hypotheses about the mean, this is the thing of interest, the standard error, because the standard error, again, is simply our standard deviation, our expected standard deviation around the mean. And then once we have our t-statistic, what we'll do is we'll just ask, where does that fall on this line? And think about what's the probability that we would get that particular t-statistic if indeed the null hypothesis were true. And so let's jump on in and explore the t-distribution together. Okay, as I said, there are lots of different flavors of things that are called t-tests. The thing that we just want to remind ourselves of is if we're using a t-distribution, probably makes sense that we call it a t-test. Works for me. All right. Well, let's play around a little bit and let's think about feeling good that we know how all this stuff is working. And I'm going to start here with some data. There are my data. They are in there, okay? Don't know what they are, but they exist. And that's all that matters to me. And this first kind of t-test that we're going to talk about is called a single sample t-test. And that is when you have a sample and you want to simply test some hypothesis about that sample's mean. And so in this case, we might say, okay, well, we have all these data, and we could even, if we were so behooved, calculate the mean of dat, and the mean of dat is 0.5095. And so what we could ask is, do we feel pretty good that the true mean of that population is 0? That's a nice kind of standard hypothesis testing in a t-testing framework, especially when we start dealing with z-transform data, which again is why we're going to end up loving z-transform data. But we could go ahead and we could say, okay, well, I'm going to set up this thing. I got this sample. I've calculated the mean, and I'm going to put my hypothesized value, theta, at 0. That's going to be my hypothesized value. And I'll even go ahead and I'll say that the mean, I'm going to capitalize it, probably shouldn't name an object the same as a function. I'm going to say that the mean is what? It's the mean of dat. Okay, so I got my mean and I got my hypothesized value. So I can also calculate then what? I can calculate the standard error. And we'll just call that SE. The standard error of the mean is going to be what? It is going to be the standard deviation of our data divided by the square root of, how long is that? 1920. Square root of 20. Or we could just say length of dat. Okay? So that's going to give me the standard error. And so now, if we were describing this, we'd say, okay, the population's mean is 0.5095 with a standard error of 0.2097. And now we have our hypothesized value. We would like to know, how do we feel about thinking that that mean is equal to 0? And one kind of way that you could think about that is we want to know whether or not the mean of 0.095 is significantly different from 0. Which is essentially what we're doing, but whenever I say significant, I mean to do that in an annoying way because people focus too much on statistical significance and they don't think about things like effect size and stuff. We're going to talk about that next time when we talk about power and p-values. But for now, we can ask, is the mean of this population significantly different from 0? So once we've done this, what have we done? We've calculated this statistic, the mean, and we've calculated the standard error. That's a statistic, right? These are all just estimates of the reality that we cannot know. We are now removed from our data. Our data are not going to play a role in this whatsoever again, because now we're doing a statistical analysis, which means that we're analyzing our statistics as opposed to truly directly analyzing the behavior of our data. And so the first thing I would want to do, or at least I would want to do, is I would want to pop, I got to figure out what way to move that way. I would want to pop it into this, right? I want to calculate a t-statistic. So I'm going to take the mean minus theta divided by the standard error. So let's go ahead and we'll do that. I will do that. I'm going to call it t-stat. T-stat is going to be what? It's going to be the mean minus our theta. And obviously, since our theta is 0 here, We obviously could have just said dropped theta from it, but we'll leave it in there for now. Mean minus theta, and then divided by the standard error. So what the heck did I call that? I called that SE. That was clever of me. Feeling on top of the world today. Okay, so here's our t statistic, 2.4296. And what we're going to do is we're going to ask, well, what is the probability I would get that? Remember that the t distribution is the sampling distribution for the means. And right now, our t statistic is somewhere over here at, what is it? 2.4, right? That's our observed value. And so what we're going to do is we're going to ask the computer very kindly. It's always nice to speak kindly to a computer. We're going to ask, what is the probability I would get that? Meaning that we are going to want it to basically integrate the area on either side of it, depending on how we want to think about it, and give us an idea of what the probability mass is. Okay, so in this case, what we'd probably do is use the cumulative distribution function for a t all the way up to 2.4. So it would go from negative infinity to 2.4. It would integrate all of this area, and then we would take that value minus 1, and that would give us that value there, and that would give us the probability that we would observe that t statistic if indeed the mean was 0. And so now let's do that. So what was that? So what we can do now then is let's call up the cumulative distribution function for a t distribution, which is pt. And then the quantile will equal our t dot stat. And now the degrees of freedom. So recall that the length of this, there were 20 pieces of information in our data, which means that, well, we calculated the mean. So we only have 19 degrees of freedom. We have 19 random variables. And then I can go ahead and I could run that. And now again, this 0.9733999, that's this area of the t distribution. We want this little area over here. So we could say 1 minus that, and that is the probability that we would get something that extreme, or of that value. We could get the exact same answer had we just simply said lower dot tail equals false. And that's going to give us the same thing. Okay. But we're not really done yet, because the t distribution goes from negative infinity to positive infinity. We observe 2.4, but that means that if our mean had been shifted to the other side of 0, it would have been negative 2.4. So we have to deal with the fact that because of how we've worded our hypothesis, we've asked whether or not the mean was equal to 0 or whether or not the mean was different from 0. We didn't say whether it was greater than 0 or if it was less than 0. We included both. We said, is it different from 0? So to do that, we'll take this p, this probability here, but we're going to multiply it by 2. And so that is our p value. And it's our p value, meaning that if the null hypothesis were true, that is the probability that we would get a value of 2.429 or more extreme. Okay. So why did we multiply it by 2? Because this can throw people off, and I'm sympathetic to that because it is kind of weird. But I'm going to draw a pretty picture, and hopefully that'll make everything make sense. Let's see. Ooh, look at that pretty picture Jim made just for your enjoyment. So originally, when we got the value of 0.0126001, that was asking basically a one-tailed hypothesis, because our t value was positive, and because this integral was happening over here, we had our critical value here, and it was giving us the probability that we would get a value that extreme or more extreme. right? Remember the whole thing of like, you know, what's the probability that you would get an individual of this value or greater, or this value or less? You know, when we were playing around with discrete distributions, as well as when we were playing around when we were introducing ourselves to the normal. And so this is a one-tailed test, and that's telling us the probability that we had a value that large or larger. But we want to account for the fact that how we've worded our hypothesis, we're just interested in knowing whether or not the probability of it being that extreme or not. So it could have been extreme on the negative side just as easily as it could have been extreme on the positive side. And so the one-tailed test, all of this probability mass is down here. And so if it's a two-tailed test, we want to take half of this probability mass and put it over to the other tail. So that way 2.5% of our probability density is on one side and 2.5 of our probability density is on the other side, and then the 95% probability is in the middle, okay? And then whether or not you want to do 95 or 99, that just affects like what your threshold is for significance. But that's why we have to multiply it by 2, because this right here, this is a two-tailed test. Like this is just a one-tailed test. And we could actually coerce R. Where is that? Yeah. To do that, well, first let's just talk about how would we set this up so we don't have to do all this. Like it's really important that you understand what the heck the t-statistic is coming from, because there could easily be opportunities in your own work where you're going to have to do this stuff by hand because there might not be a canned computer program to do it for you. But for something as simple as this, where we have our data and we want to test a hypothesis about it, we can ask R to do that for us. And there's built-in function in base R called t.test. How about that? And then what do we give t.test? We give t.test our data. Okay. If we look here, let me do question mark t.test. The default is 0. So here they're saying mu equals 0. That's our hypothesized value for the mean. That's what theta is. Okay, so our hypothesized value is 0. That's the default. So I don't even need to fill anything in for that. But I have to think about this, the alternative. And so if I were to say alternative equals greater, now it's saying that it's describing that the true mean is greater than 0, and it's still calling it here a one-sample t-test. And that is the original p-value that we got when we just simply did it this way, right here. But again, that's a one-tailed test. We don't really want to do a one-tailed test, at least in this situation. We're not interested in doing a one-tailed test. We want to know whether or not the mean is different from 0. We don't care if it's greater than or less than. We just want to know if it's different. And so again, that's where we would multiply these by 2. Nope, not there. That won't work. Let's go down here. My order of operations is messing with me. And so here's the p-value if it's a two-tailed test. And that is the default. The default is two-sided. It's the first argument down here in the help file in the lower left-hand corner, right over there. So we could be explicit if we wanted to. We could say two-sided. And we go ahead and we run that, and there it is. It's telling us it's a one-sample t-test. The alternative hypothesis is that the true mean is not equal to 0. And look, it's even given us 95% confidence intervals. And it's giving us our mean. But, you know, it's also giving us our t-statistic, which we calculated by hand. That's the same t-statistic that we got when we did it, I guess, by hand using the computer. Degrees of freedom is 19. We had 20 observations. We had to estimate the mean, which means that we no longer have 20 random variables. We have 19 random variables. And then here's our p-value, 0.0252. And so if we were to stick with the cutoff of an alpha of 0.05, we would reject the null hypothesis and accept the alternative that the true mean of the population we sampled this from is different from 0. And again, it's the default, so if we had just put our data in there, we get the exact same answer because we're just going back to the defaults. But where it mattered is if we wanted to do that one-tailed test, if we wanted to ask if it was greater than 0. Usually for most of the statistics that people do, we do the two-tailed hypothesis test because we might not have any a priori idea about whether or not we should be testing, is it greater than or less than 0. If you do a one-tailed test, then we could have a sample that was extremely lower than 0, say, and in our example here, it wouldn't show up as being significant. So let's go back to alternative is greater. Let's make it the alternative is less. And now we fail to reject the null hypothesis. And that's because we weren't even exploring the possibility that we would have a t statistic that was less than 0. So you have to be careful with one-tailed versus two-tailed test. Most of the stuff that you will encounter in your life, I'm assuming, because most of the stuff I encounter in my life, and I do a lot of statsy stuff, you're interested in the two-tailed test. So you're allowing it to either be greater than or less than. And so we could also, though, we could have a different hypothesized value. Let's say that we have our data, again, we have our data, we have our mean, and we have our standard error. And let's say that we were interested in testing a hypothesis of whether or not we think that this mean right here, 0.5095, is significantly different from a mean of 1. And so we could put that in there, mu equals 1. It's the same thing as saying theta equals 1. So we can go ahead and we can pop that in there. And yep, it is significantly different from 1. So we know it's significantly different from 0 and it's significantly different from 1. You could put any kind of number in there that you wanted to and see whether or not you think that your mean is significantly different from that value. So yeah, as long as you understand what the heck the t distribution is doing, you should be pretty golden with thinking about how we can use the t statistic to test hypotheses about a sample. So let's go on to the next kind of commonly used t-test. Right, the next commonly used t-test is what's called a paired t-test. And a paired t-test is appropriate when you have samples that are paired. How's that for helpful? But by paired, I mean like it could be the same subject, but maybe it's before or after. You know, you weigh an animal and then you feed it some food or something, and then you weigh an animal again and you ask whether or not the weight has changed. Okay, that's a paired sample. You've taken two measurements from the same individual and you're asking whether or not there has been any change. And so the paired t-test ends up really just simply being a single sample t-test, except you're going to run that single sample t-test on the difference between maybe the before and after, or the control and the treatment. So to illustrate this, let's look here. Let's see what we got. What did I give you guys to think about? I'm giving you lots of stuff to think about. It is t-test day after all. So I've set up a scenario here where I have a control and a treatment. And so another example maybe of a paired, here's a nice paired design. Let's say that in my basement, in my creepy house, I like to cook up lotions for them to put on their skin. And I'm really convinced that my lotion is great. And if I wanted to test like how good my lotion does at, I don't know, let's say it's growing hair. Funny how that popped into my head since I'm being blinded by my head and looking at myself in the video right now. And let's say that I created this lotion that makes hair grow, and then I found some people that were willing to be part of an experimental group. And for the paired data, I could say that I'm going to randomly pick an arm. Let's say that you're one of the lucky people. I'm going to randomly pick one of your two arms, and I'm going to put a control lotion on there, and then I'm going to put the active lotion, my secret lotion, on the other side. So I have a control group, I have a treatment group, and then here I'm just counting the number of hairs that have grown in that little centimeter where I put the lotion. And so this is paired because I've used both of your arms, but both of your arms are not independent of one another. So this is what would be referred to as a paired design. And paired designs are great because they're super powerful. But all we're going to do then, if we wanted to do a paired t-test, here we have all of our data. It looks like 19 of you were willing to take part in this study. Yeah, good for you. Because, spoiler alert, I wasn't paying. You just volunteered. And so there's 19 lucky people who got to be part of this study. And then I counted the number of hairs on the control arm and the number of the hairs on the treatment arm. And then I want to know, does my magical lotion do anything? Is it good? And so what I can do is I will create a new vector that I will call diff. And it'll simply be the difference between the control group and the treatment group. Okay? Just those differences. And so here's all the differences. Right? There's a couple where it didn't seem to work as well as I had hoped. But then there's a couple where it's like, look at that first individual. They got a lot more hair after they put the lotion on. So that's pretty cool. And so now we have this vector of values that are simply the difference between the control group and the treatment group. And you could have flipped it around. You could have done treatment group versus control group. It doesn't matter. But we started with 19 individuals. And now we have 19 pieces of information that we have taken from those individuals. And again, it's the difference simply between those two groups. And so we can do as we've done before. We can think about the mean difference is going to be the mean of what? It's going to be the mean of diff. Isn't that what I called it? Yep, the mean of diff. We can also calculate the standard error of diff, which is what? It's the standard deviation of the difference divided by the square root of 19, right? We decided there were 19 people that were lucky enough to do this, and you really are lucky. Okay. So that's the mean difference, negative 1.052. Here's the standard error around that difference. And so now all I want to do, it's a single sample t-test, right? I'm just asking, is the mean different from 0? Because if there's no effect of my treatment, I would expect on average the difference between the control group and the treatment group, on average I would expect there to be no difference. That's 0. And so all I would need to do is say t.test on my difference, right? Which is just these data right here. And I'm going to say mu equals 0. And there we have it. It's a one sample t-test. There's the p-value. I am going to sadly have to go back into my basement and see if I can come up with something better, because clearly I'm not very good at growing hair. So I might, back to the old drawing board. The other way that we could do this exact same test is to use t.test function, and we could give it the control and the treatment. And then I have to tell the function paired equals true. By default, it's assuming that it's not paired. And so by saying paired equals true, this handy little function will do this arithmetic for us. So it's going to calculate the difference between these two, and then it's going to do a single sample t-test. And so let's go ahead and we can run that. And what I want to point out is the p-values are the same. Here we did it as a one sample t-test, and the p-value and the t-values are the same as it is down here, except here R is telling us that it's a paired t-test. But again, p-value is the same, degrees of freedom are the same, the test statistic is the same. Everything is the same. it's two ways that you can do the exact same thing. So you can either calculate the difference on your own if you wanted to, or you can use the built-in argument paired equals true. But that's all a paired t-test is it's just a simple, straightforward, single sample t-test, except you're doing it on the difference between the two groups. Okay. All right, the last kind of t-test that I wanted to talk about is the classic t-test, probably the ones that maybe you've even done before in other classes. And this is when we're interested in asking whether or not the means are different from one another. So we have two samples and we want to test a hypothesis about whether or not we think that the mean of this group is significantly different than the mean of that group. Okay? Again, we're thinking about a location parameter, we're thinking about means. And so obviously the t-distribution will pop on into your head and say, I bet this is going to be based on a t-distribution. And so let's think about how we would do that. I'm going to move myself again. And then the data will all be up there above me, looking at it in all of its glory. And so let's say we have these two different samples that I'm cleverly calling x1 and x2. So we have two different samples that we've gone out and we have collected. And where are our data? There's the data for x1, there's the data for x2. And we want to calculate whether or not the, or we want to do a statistical test to determine how confident we are that the means that those populations were drawn out of are actually the same population, or whether or not they have different means. And so as before, we're going to calculate a t-statistic. And just briefly to think about what we're going to be doing, we're going to say we're going to calculate our t-statistic, where we're going to ask whether or not we're going to look at the difference between the two means divided by the uncertainty, well, let's just draw it, the variation in the variation between those differences. So we can think about this as the variability of the difference. Okay, so that's how we're going to calculate our t-statistic. Essentially the same way that we calculated our t-statistic before, right? Even with a single sample t-test or a paired t-test, it was always about the difference between something that's observed and some hypothesized value divided by the variability of that difference. And that's essentially what we're doing here, except here the hypothesized value is still 0. That would be the null hypothesis that those means are the same. And so we're just looking at the difference between those means, and then we're going to divide it by the variability of that difference. And in the handout, is it still called a handout? I'm not physically handing out anything. We can look at this as t again is the difference between groups, and then this is the variability, and then divided by the variability of that difference, and we can calculate it here. So the mean of group 1 minus the mean of group 2 divided by, then we're going to have to come up with some estimate of the pooled standard deviation divided by, or multiplied by the square root of 1 over n, the first group, the number of samples in the first group, plus the number of samples in the second group. And we calculate this pooled standard deviation by simply taking the sums of squares here of the first group and then dividing it by n minus 1, so that this over here should look like the variance of the first group. And then over here, this is how we would calculate the variance of the second group, right? So we're taking all the sum squared deviations from the mean from the first group plus the sum of all the deviations from the mean in the second group, dividing it by the total number of observations, and then we take the square root of that, and that's going to give us our our pooled standard deviation. All right. So we have that. We should feel pretty good about that. And so let's go do it. Here's our two groups. We have the sums of squares of x1 is what? It's going to be the sum of x1 minus the mean of x1. And we're going to square, because otherwise they'll cancel each other out. And then we can take the sums of squares of x2, which is going to be what? It's going to be the sum of x2 minus the mean of x2 squared. So now we have our sums of squares of x1, our sums of squares of x2. What kind of degrees of freedom are we dealing with? Degrees of freedom are going to be the length of x1, so it's going to be the number of observations here, which is 10, I believe. Length of x1 is 10, length of x2 is 10. And so our degrees of freedom, we've estimated two means, right? We've estimated the mean of group 1 and the mean of group 2. So we might have started in total with 20 random variables, but we estimated two means, so now we only have 18 random variables. And so the degrees of freedom then are going to be 20 minus 2, which would be the same as 10 minus 1 plus 10 minus 1. And so let's calculate our pooled standard deviation. And our pooled standard deviation is going to be what? It's going to be the square root of the sums of squares associated with x1 plus the sums of squares associated with x2. That is called sums of squares, thank you, x2. And then we will divide that by our degrees of freedom. And so now we have a pooled standard deviation. And now we need to calculate the pooled standard error. So that's going to be the S dot pooled. This is going to be the variability of this difference. Times what? Times the square root of what? Of 1 over 10 plus 1 over 10. And that's going to be our pooled standard error, or we can think about it as the variability of this difference. But since we're talking about the means, we must be talking something more similar to the standard error of the mean as opposed to the standard deviation. So now we have all the bits that we need to calculate our t-statistic. And so where is our t-statistic? That is going to be t-stat. T-stat is going to be what? It's going to be the difference between those two means. So it's going to be the mean of x1 minus the mean of x2 divided by the standard error, the standard error of that difference, the variability of that difference. And so now we have, making sure that I've done all this correctly, now we have a t-statistic, and now we could ask, what is the probability that I would get a t-statistic that extreme or more extreme if the null hypothesis were true, that the means of those two populations that we sampled from were actually different, or were the same. So we got our t-statistic, so now we can use the cumulative distribution function for the t-distribution. We'll give it our t-statistic. We have 18 degrees of freedom, again, because we lost a degree of freedom when we calculated each of those two means. We started with 20 observations, now we have 18 random variables. And then again, that should be 18, and then again, we're gonna multiply it by 2 because it's a two-tailed test. We set up this hypothesis as asking, are the means the same or are the means different? Not if this mean is greater than that mean or that mean greater than this mean. It's a two-tailed test, so we're going to multiply that by 2. And there is our p-value. So then we would reject the null hypothesis that they are sampled from populations with the same mean and accept the alternative that the means are different. And of course, we would never have to do all this by hand. because we can use the t.test function. The t-test function. And what do we put in there? We put the first group, and then we put the second group. And then for this one moment right here, so that way we get the same answer that we got up here, I'm going to say var.equal equals true. And look at that. We get the exact same value. There's the same p-value, 18 degrees of freedom. There's the same t-statistic. And so we, again, same thing. We would reject the null hypothesis that the means are the same and accept the alternative that the means are different from one another. Now this is the classic t-test, and this is the t-test how you know, most people, I guess my age or older, probably learned the t-test. But that's because back in the old days, when you calculated a t-statistic, you would go to a book and you would look in the back of a book, and in the back of that book would be a whole list of critical t-values at a given degree of freedom. What value does it have to be greater than to be significant at 0.05 or at 0.01? And so you would have to just kind of look through, and it was all based upon you know, degrees of freedom that are integers. But now that it is, I don't know, it's the 21st century, kids. Let's do this. We don't need to put that. The default in the t-test function is var equal equals false. Okay, you can see it right down here in the help file again. Let's go back down to this little help file. Var equal equals false, which means that we are going to assume that the variances are not equal. So when we came up with a pooled variability, we were assuming that the variances between x1 and x2 were identical to one another. We're not going to do that anymore. We're going to go ahead and run it. And first I want to point out that it didn't really affect things much in our case, right? Our p-value got a little bit higher, but here's the thing. Notice that our degrees of freedom now. We no longer have an integer. And so what we're doing, what R is calling it a Welch two-sample t-test. It's also called the Welch Satterthwaite correction for unequal variances. And I'm going to just show you what the equation looks like so that you can see that it does exist. There is the equation. And what it does is it takes into account that the variances might be unequal, and it essentially punishes you more degrees of freedom. And so we know that in reality we have 18 degrees of freedom because that's how many random variables we have left over. But if our variances are different from one another, we're going to get punished a little bit more, and we're going to lose a little bit of that power to detect the difference because we're going to reduce the degrees of freedom. And so this little piece of arithmetic right here is what's called the Satterthwaite or the Welch-Satterthwaite correction. And it's going to reduce our degrees of freedom ever so slightly because our variances are different from one another. Okay, so we're no longer going to be operating under that assumption that the variances are different from one another. And in the code that I've made available to you, we actually do all of the long computer code little bit there just to show that we can calculate this same degree of freedom just like the function did in R. Okay, so again, this is the classic t-test where you assume that the variances are equal, but now that we have computers and we can figure out the exact shape of a t-distribution with 17.959 degrees of freedom, you would never see that in a book, right? I mean, they would have 1 through maybe 100, and then they would start going by tens. You know, it was much more kind of coarse-grained compared to what we can do now with computers. So now with computers, by default, if we're doing a t-test and we're comparing things and we know the variances are different from one another, we're going to just boink, we're going to punish ourselves a little bit, and we're going to take back some degrees of freedom. And just to see how big of a difference this can make, I'm going to simulate some data, because again, Jim loves to simulate data. But I'm going to just simulate some data where I'm going to compare these two groups, X and Y. X is going to be drawn from a standard normal with a mean of 0 and a standard deviation of 1. The second group is going to be 50 draws, but the mean is going to be 2.4 and the standard deviation is going to be 10. So it's a population that has a much wider spread. So I'll go ahead and I'll simulate those data. And now we can say, okay, I'm going to do a t-test where it's x and y, and let's again say, just for fun, var equals true. Again, very rarely will you ever want to type that. But I do that, and okay, that makes sense. We got 98 degrees of freedom because we started with 100 random variables, and we've estimated 2 means, so we lose 2 degrees of freedom. We got 98 degrees of freedom. Now, what happens if we were to say that variances were not equal, which again is the default? This time, let's just go ahead and make it super explicit for ourselves. Now notice what happened to our degrees of freedom. They've gone from 98 all the way down to 50. So we got punished pretty hard because our variances were so different between those two samples that we're going to dock ourselves a lot more degrees of freedom. And in fact, if we were very, steadfast that significance only happens if it's 0.05 or less, we would fail to reject the null hypothesis. And we would say, as far as we can tell, they are not different from one another at an alpha of 0.05. We're going to talk about p-values next time. Never be tempted to say marginally significant, because that doesn't mean anything. We are totally arbitrarily saying that 0.05 is our magical cutoff, and we either got it or we ain't got it. And so in this case, failed to detect an effect, and so you fail to reject the null. So you have to conclude that the means are the same between those two. So I wanted to point that out because we have talked about degrees of freedom, and hopefully you feel comfortable with why we're keeping track of degrees of freedom and what they're doing. They're really keeping track of the number of random variables we have. And it's kind of easy to understand then why we would have 98 degrees of freedom here. But I wanted to point out this correction that is done with some tests, the t-test being one in particular, where we do this correction for degrees of freedom that accounts for the unequal variances. And I wanted to point this out because sometimes then if I hadn't, then you would start seeing things popping up where the degrees of freedom is 50.69. You'd be like, how in the heck is that even possible, right? Because all I'm doing is counting things. They should always be an integer. And it's true if we're keeping track of the number of degrees of freedom that they will always be an integer. But here we're giving ourselves a little bit of an extra punishment for the unequal variances, which is lowering our degrees of freedom. And the lower the degrees of freedom you have, the less likely you would be to find a difference between two groups because you have essentially less information. Okay, and so that's what I wanted to do there. The last part of the notes that, or the code that I've put up there, as well as the handout, talks briefly about non-parametric analyses. And non-parametric analyses should be thought of as a last resort kind of thing. And especially in the 21st century, there's very few reasons why you would ever consider using a non-parametric analysis. But they're called non-parametric because they're distribution free, which means that you don't have to assume anything about the underlying sampling distribution. You don't have to assume normality, for example. And that's great, and you can already imagine if the data is such a mess that you can't put it to any kind of a distribution, you would have to use then a non-parametric test. And non-parametric tests tend to be rank-based tests. So again, when we were talking about transformations, non-parametric test, it's the nuclear option, where you've rank transformed your data, so you can't really say anything about the magnitude of differences. All you can say is yes or no, according to this, were they significantly different? And that is not terribly satisfying. You're not going to get any parameters that are going to be easy to interpret. But they exist. They still pop up in the literature. People still use them somewhat frequently, especially the non-parametric forms of the t-test. And so I've put those up there for you to go through. I'm not going to formally talk about them because they're really pretty straightforward. All you have to learn is the functions. There's no reason to learn the test statistics involved because every book you read about non-parametric tests, they calculate those test statistics in a slightly different way, which kind of tells me it doesn't matter. So take a look at that. Read the handout if that's what it is. And go through the code just to kind of be familiar with what they're doing. But usually there's oftentimes a better solution than doing a non-parametric test, maybe even a permutation test, which we've already talked about. You could come up with a permuted p-value, that'd be fine. And actually there's code, the code is to do a permutation test is posted as well. And so that was our introduction to t-test. Actually, that was pretty much our full-on introduction to t-test. As we'll see, we will revisit the t-test because we can use a t-test for parameters of a linear model. We'll use t-test when we test hypotheses about covariances. And so it'll pop up again, and they're all different forms of a t-test. The ones that we went over today are the ones that are classically called t-test. They're explicitly asking something about the mean, or more than one mean, two means. And again, whenever you start thinking about posing a question where it's about a location parameter, odds are pretty good that the t-distribution is a good place to start when thinking about how you're going to test those hypotheses. So yeah, t-test away, and until next time, have a good day.